for what I showed you before, especially very important for the temperature response of the planet, because they tend to actually cool up the planet by reflecting some shortwave radiation back to space. And again, it's also true for the biogeochemical cycle. So for instance, photosynthesis here on the right-hand side, representing photosynthesis and its response to water stress in particular, is really crucial to actually explain a lot of the differences we are seeing here. We had a paper showing that a few years back, led by my former student, Julia Green. So basically the take home here is that basically model physical error and biogeochemical cycle errors really lead to a lot of the uncertainties that we are seeing when we are trying to project the future. So how do we go around that? So how could we actually improve climate models? So let's just think about, say, potentially for the ocean and the atmosphere. For the land, that's going to be slightly different. One big advantage that we have is that we are dealing with fluids, right? So what we can do is we can just basically push the numerics and push the compute so that we can resolve more and more simulation. And in fact, right now, we can actually run simulations that are resolving pretty much all turbulence, which are called direct numerical simulations, but they can only be run over like a very small box, right? Because they are computationally very expensive. So we cannot really resolve very, very large eddies, right? Just small ones. But what we can do is we can actually go to slightly up in scale to what we call large eddy simulation. And in those simulations, we can resolve much larger eddies and shallow clouds. But what they need to do is they need to have a cutoff in scale. They need to empirically represent what we call a parametrization. They need to parameterize the small scale eddies, right? And then we can move up in scale, right? We can go to what we call cloud resolving models, even at the global scale. So those are some of the examples I showed you on precipitation. And in that case, because they are run at a coarser resolution, which is on the order of a kilometer, they need to parameterize even more processes, like large eddies and droplets and so on and so forth. And then we can move on to climate model, which is kind of the end goal, right? That's what we want to run. We want to run them for hundreds of years over relatively, typically at this stage, coarser resolution. And that's kind of the issue that we have, is we need to parameterize many, many different processes. And together, this leads to this compound effect of many, many different uncertainties. So how can we address that? One pretty obvious way is just more compute, right? Running this on farms of GPUs or TPUs so that we can push the climate models to higher and higher resolution. And therefore, we can resolve more and more processes, and therefore we need to rely less and less on parameterization, right? So that's been a big push by the community, and that's certainly one way forward. Another way is to actually do kind of the other way around, right? To say, can't we take advantage of those simulations that we have that are not global, but that or are relatively short in time? But can we leverage that and harvest those data sets to actually do a better job at representing parameterization at the coarser scale, right? And you could think about that, how we can leap across scales, right? And that's why we actually use that term for the center, starting from very high spatial resolution data all the way to very coarse resolution. And we could really learn from those different simulations. There are multiple issues, and we'll address and talk about some of them here. I'd like to point out, though, that it's not the panacea, right? So it doesn't mean that just pushing for resolution or emulating would just solve all of the issues we showed before. There are many processes where basically we just don't know the physics, right? And pushing the compute is pretty much useless. One example is thinking about what we call microphysics, so the formation of cloud droplets, but especially ice crystals that are very complex, and we don't really know the underlying physics, right? Or something more complicated as well, or as complicated, let's say, is the biogeochemical cycle, or thinking about hydrology over land, right? So those are things where you're dealing with the landscape, very heterogeneous, as we are seeing here. So again, there's no really ground truth, right? We just need to make up for that, and we need to empirically represent that. And here I would argue that simulations might not have the solution, but what we can use is using observations, right? In situ observations, remote sensing observations are a great way to actually learn some of those processes and better represent them. Okay, so that would be another strategy in parallel. And those two can be combined, by the way. But today let's focus mostly on the first one. We can really harvest the data revolution, right, to improve parameterization. So again, we have a massive amount of data that's really spinning across the Earth, that is observing many aspects of the Earth, and so we can really leverage that data. We also have high resolution simulations that you can see here in the middle. This is a global kind of storm resolving simulation where you can see all of the details of like thunderstorms and clouds and synoptic events. And we can leverage that to actually better represent clouds, and especially what we call deep convection, so deep clouds, precipitating clouds at the coarse resolution. And of course, we need to be efficiently using those data sets. And for that, AI is showing that we can actually harvest many complex data sets. And it's really transforming many aspects of science. So it goes without saying. A couple of years back, we had to convince people. I think that goes without saying. So how can AI actually improve climate process simulation? So I'm going to show you a few examples, and then we'll get from that and show that it's not just about emulation, but it's also about new understanding idea. So what we'll be doing is trying to look at high resolution simulations or observations. And typically, those simulations or observations will be taken at much finer resolution than what we have in global climate models. And we'll try to coarse grain that to the same scale that we have in the climate model. And then we'll try to predict, the same type of things we are trying to predict and that we have access to in the high resolution simulation. So really what we're trying to do here is very simple. You could say it's just emulation at a coarser resolution than what we have in the high resolution simulation or in the observation. Okay, just some sort of coarse graining and emulation at the coarse grain. So. And we can do that, and we can use data for multiple things. So just to show you a little bit what we are up to these days, especially in the center and in my group, I just giving you a little bit of a flavor. So, for instance, you can use that to look at phenology, so leaf out and senescence. We have great data these days. We have a lot of satellite record going over 40 years, if you can actually make them homogeneous. And you can really start thinking about spatial and temporal anomalies. And those processes are really critical to regulate carbon cycle, but also to regulate the momentum, like the shear that we have from across the season. We can look at land-atmosphere exchange. So basically how evaporation and photosynthesis are being regulated by small-scale stomata, like pores that are located at the surface of the leaves. And we can actually show that AI can do a great job here, especially combined with physics, to do a good job at actually predicting evapotranspiration and carbon fluxes. We can look at wildfires. So wildfires are notoriously difficult to represent, but we can actually use stochastic type machine learning to do a much better job at actually predicting burned area and fire hazard as well, and basically the triggering of fire, and that tends to work quite well. We can look at things such as snow-water equivalent, which is very important for water resources as well. Models tend to struggle because the timing of snow melt tends to be very difficult to get right because of the complexity of the snowpack and the physics there. And actually AI aided by physics can do a great job there to actually predict very, very accurately the timing of snow-water equivalent and therefore like the amount of snow that's being melted. We can look at turbulence, thinking about how updrafts and downdrafts are being organized, and we can actually use that for not just predicting turbulence in the boundary layer, so the lower part of the atmosphere, but also to better understand how that's actually functioning. We can look at radiation. So that was actually the first use of AI or machine learning to emulate radiation because it's very costly. And that was used at ECMWF, the European Center for Medium Weather Forecast, to accelerate the radiation because that was taking a whole lot of time in the model and just as a pure emulation. And in that case, we are trying to do not just the simulation of radiation, but trying to think about the effect of clouds specifically. So how are clouds and small scale structures actually affecting radiation? But for today, I'm going to be talking mostly about clouds and how we can actually do a better job at representing clouds in coarse scale climate model. And I'd like to emphasize that none of the processes I mentioned here, except for like deep convection and deep clouds, are actually resolved in high resolution simulations, which we call cloud resolving or storm resolving models. So even at a kilometer scale, which is a big push of the community, we're not resolving many key processes. So we still need to actually do a better job at many of those processes. So again, pushing for resolution alone is not the panacea, and that's something to keep in mind. So we are going to talk quickly about convection, so deep clouds that are precipitating. And we'll try to say, how can we actually use AI to do a better job at representing those? And what we'll use is basically that type of simulation, so a high resolution cloud resolving model, which is on the order for the resolution of a few kilometers. And we'll use that as training data, and we'll coarse grain that again to a scale that's more similar to the resolution of the host climate model, which is on the order of hundreds of kilometers. And basically, this is standard supervised learning, you could say, and we'll use that to define the closure or the so-called parametrization. So this was one of the earlier papers we had on that front. Again, pretty simple. You take the coarse scale model state, so temperature at different levels, humidity and wind at different levels at the coarse resolution. And what we are trying to get is actually predicting the tendency of temperature and moisture, again, across those different levels. At first, we just use some deep neural network. The details are here, and we were trying to predict this coarse scale tendency and those fluxes. And the main take home is, if you look at the bottom here, this is the mean temperature state across different latitudes in an online setting. So in that case, there's no real geography, just purely ocean. We could actually do a very good job at actually predicting the temperature latitudinal and zonal response compared to this high resolution simulation. So you could see that there's really minimal bias here across most of the atmosphere. And that's very different from a standard parametrization, which is this control CAM, the community atmospheric model, which tends to have many strong biases, especially this double intertropical convergence zone, which is a very standard issue that most of those models have. And you can see that many of those issues are actually being resolved here. And this is online, I should mention, where we actually plug that neural network directly into the host model and we let it live its life, right? So it's fully interactive and resolving those things. And that's why we cannot really look at snapshots to snapshots, but we need to look at statistics, how are things actually functioning in the long run. But we were quite excited when we started to look at that. This is here looking more at snapshots with a real geography where we are running the simulation at every time step, every 30 minutes. And here you can see the truth at the top here. Again, this high resolution simulation, which is coarse grain here, and the prediction of the neural network here at the bottom. And you can see that there's very strong agreement between the two, whether that's for the moistening rate in the atmosphere or for precipitation at the surface here, which is pretty accurate, you could say. I'd like to point out is that there's only one difference here. So it looks very accurate, except for the fact that the top simulation here, so this high resolution simulation, tends to be more stochastic, right? You can see a lot of variability here that the neural network is not capturing. And you could say it's pretty obvious because the neural network by definition is deterministic, right? It's a deterministic mapping, so it will tend to smooth out that noise, right? So that noise is actually missing. And that might be important. It's not really noise, it's actually a signal. And we could actually move forward. So it's not just this offline simulation snapshots to snapshots, but we can start looking also at distributions, so the extremes I was mentioning earlier, where we can look at how is the neural net actually reproducing those extremes. So this is the high resolution simulation here. And the neural network, again, living its own life, coupled to the host model. So this is what we call an online global simulation. Is doing a great job in terms of reproducing those extremes, especially compared to a standard parametrization, like a standard closure for the representation of the convection. So for us, that was quite exciting to see that. And that was on the left-hand side, again, the case of just a purely ocean simulation. But even when we look at a land and real geography simulation, we can correct some important issues that we have in standard climate models, such as something as simple as the diurnal cycle. And in fact, if you look at standard climate models, they tend to actually rain at the wrong time. So this is here precipitation over the US. you can see that you tend to have this peak in rainfall typically around noon or slight early afternoon. And that's not at all what we're actually seeing in observations and in high resolution simulations, where you can have, for instance, mesoscale convective systems passing over the US. And this is something that we can now reproduce actually using this machine learning emulation. So we believe this is quite exciting, and that's a major improvement in terms of the quality of climate models. So seems to, I would say that machine learning seems to be really successful, and I would say it's getting more and more realistic in the sense that now it's actually not just a proof of concept. Many of those things are running online. They are coupled to the host climate model. So many of those processes can really be improved using AI, and it's more than a proof of concept at this stage. But there are still several issues, and I would say that potentially, to me, I mean, there are some potential issues related to stability, whether when we plug a neural network with a physically based simulation, is that stable or not? So those are definitely issues. But potentially the main issue that we might have is what we call out of distribution prediction, right? So, and the main point being here that we are trying to predict climate change and project the changing climate, which is kind of the end goal, right, that we typically want to have. And oftentimes what this means is that basically the training data that we typically had in the past is really struggling to actually do that, right? Because we've never seen conditions like that. We might not have seen precipitation that intense into the future. So how can we actually solve that? And so that's a strategy that a postdoc in the group, Aziz, has been working on, which is this so-called multi-fidelity approach. And really what we are trying to do here is trying to kind of get the best of both worlds, where what you have is you have basically a standard parameterization. So you could think of that, it's your physical model. It's pretty ad hoc, pretty empirical, but it has some skill, right? It has some capacity to extrapolate beyond the training data because it has some physical flavor, right? And what we are doing is we are basically correcting that and correcting the structure of that model using a high fidelity correction, which is this basically training on the high resolution simulations I showed you before. And we typically only have that in the past, right? In historical or over very limited time domain, right? So we don't have the full simulation actually observing the future, right? So we have future and past for the low fidelity parameterization, but we only have the past typically for the high fidelity correction, right? That could also be coming from satellite observations, right? And when you combine those two together, you're really getting the best of both worlds, right? The capacity to predict and to extrapolate coming from the physical component, and kind of this nice tweaking due to the high fidelity correction, which is based on very high quality data in the past. And to show you that it works, so if we look at just a projection in something we've never seen in the past, which is a warming, so we just do a warming scenario in a high resolution simulation of 4 degrees Kelvin, so pretty intense. When we look at the single fidelity simulation, which is basically this high fidelity component just alone, right? We trained, same case I showed you before, we have basically an emulation of the high resolution simulation, but just in the past, right? So we have this high resolution historical emulation, and we just want to see how good is that when we bring that into the future. And the main point here is that the R-square is actually very low. In fact, we are doing a very poor job in most regions of the globe, especially in the tropics, as you would expect, because those are the regions that are the warmest, right? The warmest ones that we have. And therefore, the model has never seen that in the past, and has no capacity to extrapolate. Interestingly, when we look at the physical model here, which is brought into the future, it's actually doing a better job than the high resolution model that's trained just in the past. So you could say that it's actually a better model, right? Even though we were so happy about the emulation based on machine learning. And then finally, what we can see is that when we combine those two together, so again, the low fidelity simulation, the physically based simulation with the correction based just on the past but not the future, together they lead to this multi-fidelity, which is able to do a very good job for basically any point in the globe except for regions where you don't have deep convection, and can do that even at very, very high warming rates, right, worth plus 4K. So we believe this is a great way to actually solve some of the issues of this extrapolation and limited extrapolation capacity of machine learning. And that's something we're actually testing now with the Blanca Balog at the Meteo France. I should mention just very quickly, I mean, there are some other strategies such as embedding also physical invariances. So that's the work of Tom Buckler, where you can actually transform your data in the past so that it looks alike in the future, right? So that there's basically no distribution shift. So those are some other tricks you could use. We call that climate invariant mapping, where there's no change as we move into a warming simulation. So that sounds great. And basically that's been kind of my journey, I would say, to the use of machine learning for climate science, except that it's been a little bit of a roller coaster, right? So initially things worked really well. We could actually emulate convection really well. We had very good success by bringing that into the model, but then we started to look a little bit more into that, and we saw that the model cannot really generalize. So it has it's really struggling for climate change type scenarios. It's struggling also with stability. Sometimes you plug a neural network and it's just going to break the whole host model. And maybe also importantly, it's missing some important physical invariances as well, right? So some physical equations, for instance, that are quite critical. And so over the last couple of years in my group and with colleagues, we've been trying to embed those physical invariances, or sometimes called equivariance, to actually basically better respect physics when we actually plug those machine learning algorithms. And we believe that this is also a good way to improve model stability, also build some sort of causality and improve generalization, as I just showed you here. But I would say maybe more fundamentally, I mean, the issue is that, okay, we can emulate processes, but what did we really learn, right? And I would say that that's been, for me, like kind of the main objectives over the last couple of years is using AI and machine learning to actually harvest data, but also understand new things, right? And I'll try to show you a few examples. So how can we use machine learning to go beyond just process simulation, but really to go to new discoveries? So there are different ways you can actually do that. You could use causal approaches, right? Where you can look at cause and effect and look at, so that's a great way to think about processes and cause and consequence. You can look at dimensional reduction. So the kind of simplest way would be to do an empirical orthogonal function decomposition UF, but you can do it in a nonlinear fashion as well, and you can create a latent space. So basically a low dimensional embedding that can actually help you understand the process better. And then you can also use some new kind of kids on the block, which are this equation discovery, right? So they are great tools now. I mean, those two or the ideas have been around for a long time, but the tools are much more mature now, and we can actually kind of discover equations from data, and that's really much more interpretable and something that people would trust a lot more than just a black box neural network. So I'll show you quickly two examples, starting with convection. So the first example is related to what we call aggregation of convection. And the main point is that in observations and simulations, convection tends to sometimes organize or self-aggregate. And you could say maybe it doesn't matter, but it does, in the sense that when convection is aggregated like here, it tends to actually rain a lot more here because there's some sort of shielding effect and clustering effect, which is protecting the precipitation here at the bottom. And therefore, we tend to have much higher precipitation rate, but also a pretty strong impact on the environment here. So for instance, if we look at this environment here in the aggregated case, it tends to have much lower relative humidity. So it's a much drier environment than what you would have at the top. And that has potentially some large impact, for instance, on climate sensitivity because of the radiation back to space, but also on precipitation. So all the reasons to actually care about aggregation. And kind of the science question we'd like to address here is really, does precipitation depends on some aggregation or something that basically we cannot capture at the coarse resolution, right? So we have the climate model at 100 kilometers or so, and we can have this subgrid scale effect, which we will call some microstate. And we'll try to see, like, do we need to actually have some information about the microstates or some information below the 100 kilometer resolution to actually predict precipitation really well, or maybe it doesn't matter at all. And kind of related to that, you could say maybe what we need is actually to also link that to what we call the stochasticity of parameterization and precipitation. The fact that people have been trying to basically represent precipitation as a stochastic process, and people believe that's very important, but it's still pretty ad hoc the way people actually represent that. How do we actually add that noise? What's the level of the noise? What's the kind of correlation across space and time of that noise? Is really a non-trivial task to do, right? So it's a very challenging thing to do. And maybe there's a connection between the two of them. It's just because when you have a nonlinear dynamical system and you just cut and reduce some dimensions, some things might appear as stochasticity, but it's just because you're not resolving all of the different variables that actually describe the system. So what we'll do again is we'll use the same simulations that we had before, where we have those high resolution simulations, storm resolving simulations. We're going to cause rain them, and we'll be looking at precipitation data here. We have about 100 million data points worth of simulation results. And the first kind of benchmark we'll have is we'll say, okay, we had the high resolution field of moisture, temperature, and the amount of water, so precipitable water in the column at 100 by 100 kilometers, so equivalent to our climate model. We are going to cause rain that to just one value for each, similar to what we have in the climate models. And then we are going to plug that into a fancy neural network and try to predict precipitation, right? So exactly equivalent to what we are doing in a climate model. And then we try to do a second thing, which is slightly more sophisticated in the sense that we'll say, maybe we're missing something at the large scale, and what we'll try to add is actually embedding some information about the structure that we have at the fine resolution, and we are going to be encoding that, so that's what we call an autoencoder. We are going to be encoding that information into just very few dimensions. So basically, this is a two-dimensional vector here, as opposed to 32 by 32. And we just want to encode this kind of clustering information here, and we are actually training all of that together, right? We are trying to reproduce the high resolution field, and at the same time, we are trying to do a good job at basically regressing and predicting precipitation. So we do that in tandem. That's what we call end-to-end training. And when we look at the baseline result, what we really have is that we have the typical issue I showed you earlier in terms of the coarse resolution model, where the coarse resolution simulation is doing a poor job in terms of representing precipitation. So this is the high resolution field, the truth. And you can see we really have the same issue. We are drizzling too much, don't have a whole lot of high intensity events. And you could actually check in time, and the temporal correlation is actually, the R square is nearly zero. We have no predictive power in time. Once we add this organization, we can show that, in fact, now we are spot on. We can actually predict extremes of precipitation really well. And on top of that, it's not just purely in terms of statistics, we really have a skill in terms of predicting in time and across space. And the R square is actually very, very high in that case. And so what this means is that to predict precipitation, we don't need just the coarse resolution field, we actually need also the fine scale information, which is this organization. And really, it's telling us that organization is a key component in actually explaining precipitation in simulations. And an advantage is because it's two-dimensional, we can actually look at that and we can investigate this two-dimensional vector, and we can actually have a look at that and investigate what is going on, and we can see that this is actually the clustering of precipitation that we are seeing here. So what did we learn here? We learned that first, organization regulates precipitation extremes and their prediction. And second, we learned that precipitation stochasticity is really mainly due to convective aggregation, so subgrid processes that are really critical to actually predict the temporal behavior of precipitation. So it's not really stochastic, it's just that we didn't have access to all of the different variables. The second example, very quickly, I'd like to show you is that we can also use symbolic regression of this equation discovery to actually start thinking about different climate processes. And this is an example here looking at cloud cover, where what we did is basically discover the formulation of cloud cover and how to best represent cloud cover in Earth system model and climate models. This is here the standard parameterization that we have in a climate model, which is called ICON. And here is a high resolution simulation from Diamond, this storm resolving simulation I showed you earlier. And this is here, you could say, the observations, the reanalysis product. And basically what we like is we'd like to actually match that observation component. And what we did is we basically trained symbolic regression, so an equation discovery on the high resolution simulations, and we discovered that equation here to represent cloud cover. And then we fine-tuned that on the observations, and we could get something that's actually very, very similar to the observations, but that's also highly interpretable and highly easy and pretty easy to actually plug in a climate model. So we are actually very happy with that and something that we can actually interpret in terms of the physics. So basically, very quick summary of the use of machine learning. So we can really use machine learning to improve climate model and to really leap across scales. And I want to emphasize again that machine learning closures now are not just a prospect or a proof of concept. Many of them are actually working now, and people are starting to really implement them at scale into a host model. So it's not a hypothesis anymore whether they are working. There are still multiple challenges. Several of them I hope I discussed today. But the machine learning is also a great tool to actually make new discoveries, especially on big data, right? It's a great summary of very complex data, and oftentimes our brain can actually not process all of that data and cannot make sense of all of that data. And that's a tool we should use more and more to actually understand, especially complex and high dimensional data. So I'd like to conclude within the next 5 minutes to say what are the solutions and challenges that we have to get to the next generation of climate models. So I hope I convinced you that the first solution to basically improve the quality of climate models is to use AI, right? To harvest either high resolution simulations or Earth observations. And really the main point is that it can really help in terms of the quality of the climate simulations we are actually doing. There are important challenges on the way. The first one is that climate models cannot easily integrate machine learning algorithms because they are typically based on old languages such as Fortran. And it's also very difficult to assimilate data in those models. So it's really, really difficult to harvest the data revolution right now. A second solution, the one we talked about early on in this talk, is to just increase compute power, right? By increasing the compute, we can increase the resolution. And as you can see, we can resolve more and more processes such as topography, or we talked about deep clouds. And that's just going to improve things because we're resolving more and more of many processes that are currently unresolved. But a major issue is that we really have a plateau in terms of the performance and the resolution we are achieving in those models. And a lot of that is due to the fact that we are not really using modern hardware in many climate models, such as graphical processing units, GPUs, that are used extensively in AI, or tensor processing units also used by Google, for instance, for AI type algorithms. And it's really a lot of that is due to a legacy of low-level Fortran code that's really not agile to different hardware, right? And that leads to really this plateau in performance. So we need to be a lot more agile because we have many different processes that are playing a big role. A third solution that we have is to actually accelerate progress. And basically, people have lots of great ideas, especially students. But the main trouble is that models, again, are based on old programming languages such as Fortran. So they are not really very inclusive of the younger generation. And those folks and students and postdocs mostly know Python, right? So that's a huge barrier to progress, right? So people have ideas, but it's very difficult to actually implement them. And finally, to improve climate projections, I didn't really talk too much about that, but what we also need is running multiple ensemble members, right? So to make sure that the results are statistically significant. And this is just an example here showing that, especially over the first few decades, a lot of the uncertainties are actually dominated just by the initial conditions and the fact that we need to run multiple ensemble members. But it's computationally very expensive to run many of those simulations, and therefore we need to have a way to actually, again, speed up the compute, right? So we can run those ensemble members at scale. So how can we get there? You know, that's kind of the question. So I would argue that what we need is actually built around three pillars, right? The first one is actually modern code and compute. And the reason for that is that when we have a Python-based code, it's going to be much more inclusive. So students and postdocs and the younger generation can actually do that much more efficiently, and they can code and try out ideas. But we also have tools now where we can actually use Python, but also have like very, very powerful compute and efficient compute, right? And one great example is so-called JAX. That's a Google interface for AI. And some people have started to code some things such as this ocean model here, the Norwegian model, where they could show that JAX on, for instance, multiple CPU was almost as performant as Fortran. And that's a Python-based code. And you could also leverage GPU almost for free, right? I mean, it's very, very straightforward to just run on GPUs, whereas it requires a whole recoding of the Fortran-based model. So that's a huge leverage to actually leverage new type infrastructure and hardware. And you could say that for that, like, how do you get there? We had a student back in the summer that we were co-advising that showed you could actually use also large language models. So this is just an example here. You can use large language models to actually convert parts of the code. And this worked really well. So he did that for part of the community or system model. And you could show that you can actually generate some unit tests, and you can actually generate some Python code that is similar to the Fortran code, and then generate a bunch of unit tests and test that. And you fail multiple times, but eventually the code will converge and will perform and pass the test. And in that case, you have a successful model and you have a Python-based model. So that was based on JAX. And we could show that with that model, we could actually have very high performance, which was equivalent and even faster than the original Fortran model, because we could leverage GPUs that we don't leverage right now. Oh, sorry, I have some. The second thing that we can do, and I mentioned that earlier in the talk, is just having this kind of seamless AI integration, right? So AI can really leverage and improve the representation of many physical processes. And we have this kind of modern code, which is really the essence of AI-based tools these days. We can really build this kind of hybrid system model, which is reunifying physics and AI. And finally, with those tools, what we can do is basically harvest global observations at scale. Doing data assimilation becomes pretty straightforward because many of those tools have what they call some automatic differentiation. And that's one example we actually we are developing for the carbon cycle, where we have a platform that's actually doing all of that, where we can actually plug in some neural networks and harvest data at scale, leveraging basically tools developed for the AI community and this automatic differentiation. So basically, we can look at the sensitivity of any type of output to some model variables or some model parameters, and we can fine tune that, and we can even use Bayesian uncertainty quantification for that. So those are great tools that can really leverage the type of things we have and can really push the compute, but also the integration of AI and observations to lead to a new generation of climate models. And this is basically a paper we submitted with my colleague Veronica Eyring and some other colleagues, kind of showcasing this vision for the next generation of climate models, where we have those hybrid models that have a lot of AI into them, but also like a lot of physics as well, and leveraging a lot of the high resolution simulations and the observations to lead to basically the best quality type models that we want, along with, if needed, some regional nesting or downscaling, which could also be machine learning based. In fact, there's a lot of development in that space, so that we can actually drive impact models, which is what we want in the end. So with that, I'll leave you here and happy to take any questions.
Thank you very much, Pierre, for this really, really interesting and exciting talk. So floor is open for questions to the audience. Yeah, we encourage you to just ask a question or alternatively put them into the chat. And maybe to give people a little bit of time to think about their questions, maybe I can ask you one, sort of start with one.
Sure.
In several places, you sort of distinguish between offline and online incorporating of machine learning models. And there's sort of slightly different definitions of what we exactly mean by that. Could you elaborate a little bit?
Yeah, that's a great point. So what we call offline and online is not like in machine learning, which is offline training and online training. In that case, what we mean is that for offline, we mean it's basically a supervised learning task where we have some labeled data and we just try to reproduce that. The online version is we take that neural network typically and we plug that into the host model, right? So in that case, they live their lives and typically they crash. But now we have more and more strategies to avoid that crash. But that's what we mean by online. It's not to be confused with what we call online training, which is basically learning on the fly. And there's a lot of confusion. If it were me, I would not use the term online. It's just people use that. I don't like that term. It's confusing.
So there was no online training in the
No,
example.
there's no online training. But in the last slide or last but one I mentioned, really the idea of this data assimilation is really online training, right? So things you can do on the fly, that's the objective. But for that, you need really modernized infrastructure, right? You need to have the tools that allow you to do that. So it's a huge undertaking, but it's quite exciting.
Yeah, great, thanks. Then I guess Cecile would be next.
Yes, thank you. This is a very interesting talk and exciting. I have a question about uniqueness. You were saying that because you had the improvement in your precipitation because of self-aggregation, that was the explanation. However, there's a lot of evidence too that if you have heavy tail distributions of vertical velocity, that can also improve the distribution of precipitation. And because these heavy-tailed student-like distributions are based on the physics of the situation, they're based on the dynamical description of vertical velocity. I mean, we tend to believe that. Not that we disbelieve the self-aggregation, but how do you show uniqueness in what you find?
That's a great question. So first off, we are actually working exactly on that. So that's a great question. Yeah, I'm actually very puzzled by that. Like, how much is kind of the dynamical component as opposed to thermodynamic and self-aggregation? So that's a great question. In what we had here, we had no information about vertical velocity directly. We only had precipitable water, but you're right. I mean, the fine resolution precipitable water field could reflect some structure, of vertical velocity, So that could be, those could be confounders, yeah. But basically, we are trying to decompose the two, yeah. So it's actually more complicated, but we are trying to diagnose what is going to be a dynamical component, what is going to be not be a dynamical component. So still open question there. I don't know yet. A great question.
Thank you.
Right, there's another question in the chat from Chetan, which is, when using AI to emulate unresolvable processes, how do you ensure that the improvements are not for the wrong reasons? Also, how do you decide which features to emulate or represent?
That's a great question. So I didn't show that here, but yes, I mean, or maybe I can very quickly show that again. So 1 second. Oh. Yeah, if you look here, basically for the neural network emulation, we can see that there are substantial biases, and we tried like plugging ozone and all that, but we could never really resolve that, and my suspicion was that, to your point, that sometimes you're getting the right answer for the wrong reason, because we plug all of those columns that are coming from all over the globe, and train a neural network, but there's a lot of like spatial autocorrelation, right? And so that's what we did. We tried to basically break that. And so we use some sort of causally informed, it's actually just published now and just out this week. But it's basically what we call a causal neural network, where we try to embed some sort of causal discovery algorithm to make sure that you don't use just mere correlations, but also use like some causal mechanisms. And that does improve a lot, because in that case, we're trying to get closer to the actual mechanisms, the right variables that are causing things. And we can actually also visualize that using explainable AI. And it makes a whole lot more sense. So we can really see the downdrafts, no spurious autocorrelation in the profile. So it's very critical, and also very critical when we are trying to predict outside of the training data, right? Because we want to get that for the right reason. Otherwise, we would fail miserably. But it's really, really critical. Yeah,
Morgan.
I was wondering what the value of DNS in the atmosphere is before we really get the microphysics right, or whether using computing power at that scale can really teach us a lot without having to worry about latent heating and cooling and stuff out of equilibrium.
That's a great question. So some of the things we're looking at are DNS for droplets, so that's a good point. The other one is for the stable boundary layer, because for very stable cases, people have shown that you need to be at very, very fine spatial resolution because you cannot really resolve the Osmedov scale. So that's a place. So that's where we're using DNS. So there's a postdoc in the group doing DNS of very stably stratified media, and we can show that it's actually important. But for the rest, I would say you're good to go with an LES.
Okay.
Yeah,
Thanks.
that's a great question.
Right. Any further questions from the audience? I hope I didn't miss anything in the chat, but I don't think so. No. Maybe if I may ask you another question, Pierre. So
Sure.
the whole idea is of course extremely tempting to use all the observational data, in particular from remote sensing, all those petabytes to train machine learning models and then incorporate into climate models. Do you have concerns that the very limited duration of the available time series could be a problem for, given all the,
So I think yes, and the second issue is that a lot of processes are not directly observable, right? So that's what I was trying to allude to at the end, is that you need to have a framework where it's a bit more connected to data assimilation, and that's exactly what we are doing for this carbon cycle model, where you might have processes, but what you're observing might be completely indirectly related to those, right? So you're observing some brightness temperature or something like that. So you need to connect that. And ideally, if you have something that's differentiable, you can actually basically optimize your model to actually best match the observations. Yeah, so that's one. To your point about historical data, I mean, I'm very hopeful with this type of multi-fidelity approach. That seems to work really well. Like every time we tried that, I mean, it's a bit tricky to handle. You need some mastery, like Aziz has, but it's great. And you can actually have also, everything is Bayesian, so you have uncertainty quantification, which is really nice because you know when you trust your results or not. And you can actually include stochasticity as well. But that seems to me a great solution for those things. Yeah, so you have this extrapolation capacity. Yeah. So I feel okay now. I was worried a few years back. I feel much better now.
Very good. All right. Okay, so if there are no further questions from the audience,
I'm
then
sorry, excuse me.
go
May I
ahead,
ask
Cynthia,
one more
please.
question? Okay, I
Please,
don't
of course.
seem to have a
Also
reaction scheme. The question
Sure,
I
go ahead.
wanted to ask is, have you considered using stochastic homogenization, which often keeps things like conservation properties in view with machine learning? It seems to me that the two of them, the fact that you could not get some of the stochastic part, and that worries me that you might be missing noise-induced drifts. Is there any way you could combine the physical stochastic modeling with your AI?
So what we are trying to do is using Monte Carlo or like Hamiltonian techniques to actually estimate the uncertainty quantification when we have those different machine learning algorithms. So I think we have now, it's expensive, but we can get a pretty good handle of the uncertainties and some of that stochasticity. Except at times, if there's a special autocorrelation, it becomes a bit more complicated. Yeah, so that's still something pretty open, I would say, at this stage. There's
okay, I would like to remind you that stochasticity does more than represent uncertainty. It's actually a physical system, and it can affect the means and all of your moments. So that's the kind of stochasticity I was wondering if you could add to your technique.
Yeah, so that's what we can do. Yeah, so we can represent this this stochasticity, whether that's actually physically based or whether it's due to the uncertainties, and we have ways to actually decompose some of the sources of variability, yeah, whether they are from like noise of the observations or whether they are physical. But I would say still the tools are pretty are much less developed than some of the standard tools, but there's a lot of development in that field.
Thank you.
Thanks.
All right. Any further questions or comments? If that's not the case, then thanks a lot, Pierre.
Thanks.
Thanks everyone for joining us, and I hope to see you, many of you, on for our next talk, which will be on, let me see, on March 4th. So we will switch generally from first Tuesday of the month to first Monday of the month. And the next talk will be on March 4 by Lei Bai from the Shanghai AI Lab on data-driven weather prediction. And I hope to see many of you there. Thanks a lot, and have a nice rest of your day, nice evening, depending on where you are. All the best.
Thanks everyone. Yeah, and I apologize for my voice again. Thank you.
Yeah, no worries.
Bye.
I hope you get better soon.
Bye. Take care.
Bye. Thank you, Pierre.